Hello dear students, today we will take some more problems based on Fourier series. First problem is expand fx is equal to mod x from minus pi to. First problem is expand fx is equal to mod x from minus pi to pi in Fourier series, hence so that 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square plus dot dot is equal to pi square by 8. Its solution is, because fx is equal to x mod is even function, of x, therefore Bn will be 0 and we have Fourier cosine series. As fx is equal to a naught by 2 summation 1 to infinity an cos nx. Suppose this is equation 1. Now a naught is 1 upon pi minus pi to pi fx dx, that is 1 upon pi minus pi to pi fx is mod x, this is dx. Because this is even, therefore we can write the limit from 0 to pi by multiplying here by 2. So this is 2 by pi 0 to pi x dx, which gives 2 by pi x square by 2 from 0 to pi. This is 2 by pi square minus 0 square, and we get pi square by pi means pi. Now an is 1 upon pi minus pi to pi fx cos nx dx. This is 1 upon pi minus pi to pi fx is x mod, this is cos nx dx. Again cos nx is even and this is even, so this total x mod cos nx will be even, and we can write it as 2 upon pi 0 to pi x cos nx dx. We can integrate it by parts as 2 upon pi 2 upon pi x into sin nx upon n from 0 to pi minus 0 to pi into sin nx dx upon n. This gives 0 for both limits, therefore we can write it as 2 upon n pi, 2 upon n pi, here n is common, Now this is minus 0 to pi sine, or plus minus can be written here, sine nx dx. N has been taken in common. Now integral of minus sine nx is, this is 2 upon n pi or pi n. Integral is cos nx upon n from 0 to pi. So we get 2 upon pi n square. Upper limit is cos nx, lower limit is cos 0. So 2 upon pi n square, cos nx can, cos n pi upper limit, cos n pi can be written as minus 1 to power n, and cos 0 is minus 1. So it will give 0 when n is even. When n is even, minus 1 to power even will be 1, 1 minus 1 will be 0, 0 when n is even. And when n is odd, this minus 1 to power odd will give minus 1, minus 1, minus 1 gives minus 2, becomes minus 4 upon pi n square. Therefore, equation 1 gives. Equation 1 is fx, which is mod x, will be a naught by 2. A naught has been calculated to be pi. So this is pi by 2 plus summation 1 to infinity an. An is 0. An is 0 for even number, and for odd numbers an has been calculated to be 4 upon pi n square. This is an into cos nx. This can be written as pi by 2, or fx is equal to x mod minus 4 upon pi summation n is equal to 1 to infinity, odd values of n, cos nx upon n square. Now we can expand it as fx as x mod equal to pi by 2 minus 4 upon pi. Now when n is 1, this will be cos 1x upon 1 square, cos x upon 1 square. Next odd number will be 3, so we get cos 3x upon 3 square. Next odd number is 5, cos 5x upon 5 square, and so on. This will be the required series. Suppose this is equation 2. Now in second part, if we put x is equal to 0, this becomes 1, 1, 1 and so on. Putting x is equal to 0. In equation 2 we get 0 is equal to pi by 2 minus 4 upon pi. Cos 0 is 1 upon 1 square plus cos 3, 0 means again 1 upon 3 square plus 1 upon 5 square and so on up to infinity, or pi by 2, this is minus cancels, will be equal to 4 upon pi 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square and so on up to infinity, or we get 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square dot dot to infinity will be equal to this 4 comes here 8 and this pi comes here, giving pi square by 8, which is proved. Now next question is, expand the output of full wave rectifier in Fourier series, where fx is equal to minus sin x from minus pi to 0 and sin x from 0 to pi. Solution: 0, pi, 2 pi, 3 pi and so on. This is minus pi, minus 2 pi, minus 3 pi and so on. This figure shows the graphical representation of given function fx in minus pi to pi and its periodic extension. Out of minus pi to pi. Here Fourier series will be fx is equal to a naught by 2 summation n is equal to 1 to infinity an cos nx plus bn sin nx. Suppose this is equation 1. Now we have to find the Euler's coefficients a naught, an and bn. Here a naught is 1 upon pi minus pi to pi fx dx. So it will be 1 upon pi minus pi to 0. Fx is minus sin x plus from 0 to pi fx is sin x dx. This. Now if we interchange the limit, this becomes 0 to minus pi, and when minus pi is written as pi, then minus comes here. This minus into this minus gives plus, so this becomes 1 upon pi 0 to pi sin x dx plus 0 to pi sin x dx, that is 2 upon pi 0 to pi sin x dx. This will be equal to 2 upon pi integral of sin x is minus cos x from 0 to pi. This is minus 2 upon pi cos pi minus cos 0. Cos pi is minus 1 and this is also minus 1. So this is minus 2 upon pi into minus 1 means minus 2 into minus 2. 2 becomes 4. So it gives 4 upon pi. Now we get an. An will be 1 upon pi minus pi to pi fx cos nx dx. This is 1 upon pi minus sin x, and from 0 to pi fx is sin x into this cos nx dx. Again interchanging this limit, this goes here minus pi to 0 and minus can be taken here, minus into minus gives plus, so it is 1 upon pi 0 to pi sin x cos nx dx plus 0 to pi sin x cos nx dx. So this becomes 2 upon pi integral 0 to pi sin x cos nx dx. This 2 can be taken inside to make 1 upon pi 0 to pi. This is 2 sin x cos nx dx. We can write it as 1 upon pi integral from 0 to pi sin n plus 1 x minus sin n minus 1 x dx. Because if you consider this as sin c minus sin d is equal to, this will be equal to this one minus cos n plus 1 upon n plus 1 from 0 to pi minus or plus the integral of minus sin n minus 1 x will be equal to cos n minus 1 x, here also x, upon n minus 1 from 0 to pi it will be 1 upon pi upper limit minus cos n plus 1 pi minus cos 0 upon n plus 1 plus cos n minus 1 pi minus cos 0 upon n minus 1. When n is odd, then n plus 1 and n minus 1 each are even. Each will be even. Therefore, from suppose this equation 2, therefore, hence from equation 2, n will be 0. And when n is even, then when n is even, then n plus 1 will be odd. N plus 1 and n minus 1 are odd. Both will be odd. And cos odd pi is minus 1. So this becomes minus 1, minus 1, minus 2. Similarly, cos odd pi is minus 1, minus 1, minus 2. Then equation 2 gives an is equal to equation 1 upon pi this is minus 1 minus 2 means minus 1 minus 1 minus 2 into minus gives 2 upon n plus 1 and minus 1 minus 1 minus 2 minus 2 upon n minus 1 n minus 1. 2 can be taken common. 2 upon pi n square minus 1 will be LCM. We get n minus 1 minus n minus 1. N cancels n and we get an as minus 2 into 2 means minus 4 upon pi into n square minus 1. Thus an is 0 when n is odd. An will be minus 4 upon pi n square minus 1 when n is even. And Bn will be equal to 1 upon pi minus pi to pi fx sin nx dx. This will be 1 upon pi minus pi to 0 minus pi to 0 minus sin x into sin nx dx plus 0 to pi sin x sin nx dx. Again, by interchanging the limits, we get 2 upon pi 0 to pi sin x sin nx dx, which will be 0. With these values of an, a naught, with these values of a naught, an and bn, equation 1 gives. Therefore, equation 1 can be written as fx is equal to pi. A naught has been obtained as 4 by pi. So 4 by pi upon 2. This is a naught by 2 plus summation n is equal to 1 to infinity. N for even n, an is minus 4 upon pi into n square minus 1. This is an into cos mx, bn is 0. So fx will be equal to 2 upon pi minus 4 upon pi summation n is equal to 1 to infinity even n cos nx upon n square minus 1, which can be written as 2 upon pi minus 4 upon pi. First even number is 2, cos 2x, is, this is cos 2x upon 2 square by 2 square minus 1 means 3. Next even number is cos 4x upon 4 square minus 1 means 15. Next cos 6x upon 35 and so on. This will be the required Fourier series. Next question is, expand the function fx is equal to plus 1 from 0 to pi and minus 1 from minus pi to 0 in Fourier series. Here the given function fx is odd function x. Therefore, a0 and an will be 0, and Fourier series will be Fourier sine series as fx is equal to summation 1 to infinity bn sine nx. Suppose this is equation 1. Now bn will be equal to 1 upon pi minus pi to pi fx sine nx dx, which can be written as 1 upon pi minus pi to pi, minus pi to 0, fx is minus 1 into this is sine nx dx, plus from 0 to pi fx is 1 into this is sine nx dx, which can be written as 1 upon pi if we interchange in limit 0 to minus pi and 0 to minus pi, we get or simply we integrate it. This is 1 upon pi integral of minus sine nx, integral of sine minus integral of minus sine nx is, this is 1 upon pi, integral of this is cos nx upon n from minus pi to 0, and this is plus, integral of this is minus cos nx upon n from 0 to pi this can be written as 1 upon pi, n is common, pi n, here cos 0 minus cos minus pi minus cos n pi minus cos n pi minus cos n pi minus cos 0. Now equation 1 gives fx is equal to bn sine nx when n is odd, and we have obtained bn equal to 4 upon n pi, so this will be equal to summation n equal to 1 odd to infinity 4 upon n pi sine nx. This is 4 upon pi can be taken out of summation odd n is equal to odd to infinity sine nx upon n. Now this can be written as fx is equal to 4 upon pi. When n is 1, this will be sine 1x upon 1. When n is 3, sine 3x upon 3. When n is 5, this is sine 5x upon 5. Next problem is expand the function fx is equal to x sin x as Fourier series in the interval minus pi to pi. Hence, prove that this one. Now, solution here fx is equal to x sin x is even function of x. Therefore, Bn will be 0 and we have Fourier cosine series. Fourier cosine series as fx is equal to a naught by 2 plus summation n is equal to 1 to infinity an cos nx. Suppose this is equation 1. Now we find a naught and an. A naught will be equal to 1 upon pi minus pi to pi fx dx. This is 1 upon pi minus pi to pi. Fx is x sin x dx. This is even, that is due to symmetry it can be written as 2 upon pi 0 to pi x sin x dx. This can be integrated by part as this is 2 upon pi x into minus cos x from 0 to pi minus into minus cos x dx. This gives 2 upon pi minus upper limit is pi into cos pi, pi into cos pi, and lower limit is 0. It gives minus minus plus. Integral of cos x is sin x from 0 to pi. This gives 0 for both limits. So this pi cancels this pi. We have 2 cos pi is minus 1. Minus 1 gives plus 1. So a naught is 2. Now an, we find an. Now an will be equal to 1 upon pi minus pi to pi fx cos nx dx. This is 1 upon pi minus pi to pi. Fx is x sin x into this is cos nx dx. Again this is even, this is even. So from 0 to pi x sin x into cos nx dx. This 2 can be taken here to write as 1 upon pi 0 to pi x into 2 sin x into cos nx dx, or an will be equal to 1 upon pi minus 1 upon pi 0 to pi x into 2 sin x cos nx dx. This can be written as 1 upon pi 0 to pi x into sin n plus 1 x minus sin n minus 1 x dx. Sin c minus sin d equals this much. Now, this can be integrated by part as, therefore, we get an is equal to 1 upon pi, this is u and this is v. So, x into its integral is minus cos n plus 1 x upon n plus 1, and its integral is minus means minus sin n minus 1 x gives antiderivative as cos n plus 1 x upon n plus 1 from 0 to pi minus 0 to pi, its derivative of x is 1 and its antiderivative is minus cos n plus 1 x upon n plus 1 minus its antiderivative minus plus cos n minus 1 x upon n minus 1 dx. Now, after integration, this second part will give sin term in both cases, which will give 0 for both limits. So, second term gives, this becomes 0 after integration. For both limits. So, first term only remains, we get an is equal to 1 upon pi upper limit pi into cos minus cos n plus 1 pi upon n plus 1 plus cos, this is n minus x. Therefore, an will be equal to 1 upon pi, here for upper limit pi into minus cos n plus 1 pi upon n plus 1 plus cos n minus 1 pi upon n minus 1 minus lower limit gives 0 due to this. Here 0 into something gives 0 or it can be written as an will be equal to this pi can cancel this and we get cos n minus 1 pi upon n minus 1 minus cos n plus 1 pi upon n plus 1 when n is odd, then both n minus 1 and n plus 1 are even, then above equation gives an becomes equal to cos even pi is 1, cos even pi is 1, so we get 1 upon n minus 1 minus 1 upon n plus 1 LCM is n square minus 1. Here n plus 1 minus n minus plus 1. So n cancels out and we get 2 upon n square minus 1 when n is odd. Excluding n is not equal to 1, and when n is even, then both n minus 1 and n plus 1 are odd. In this case, when n is even, then n plus 1 and n minus 1 both are odd, and odd cos odd pi is minus 1, therefore then equation 2 gives an is equal to cos odd pi is minus 1, so minus 1 upon n minus 1, and this is again minus 1, minus minus becomes plus 1 upon n plus 1. LCM is again n square minus 1, here n plus 1 plus minus n minus 1 plus n minus 1. So n cancels out and we get minus 2 upon n square minus 1. Thus an will be equal to minus 2 upon n square minus 1 when n is even. N must not be equal to 1. And when n is 1, and when n is 1, then a one will be equal to 1 upon, or a n is equal to 1 upon pi minus pi to pi fx is x sin x into cos nx dx gives, then this gives a1 is equal to 1 upon pi minus pi to pi x sin x into cos n becomes 1 cos x dx. Due to symmetry, this is even and this is also even, so due to symmetry we get 2 upon pi 0 to pi x sin x cos x dx. 2 can be taken here to get 1 upon pi 0 to pi x into 2 sin x cos x dx, and 2 sin x cos x is sin 2x. So this can be written as 1 upon pi 0 to pi x into sin 2x dx, or a1 will be equal to 1 upon pi integrating up by parts, we get this is u and this is b, x into minus cos 2x upon 2 from 0 to pi minus 0 to pi, derivative of x is 1 and antiderivative of sin 2x is cos minus cos 2 x upon 2 dx. This gives 0 after integration, because this gives sin 2x term which will be 0 for both limits. Now we get minus 1 upon 2 pi upper limit pi into cos 2 pi and lower limit is 0 due to x. Cos 2 pi is 1, this pi cancels this one and we get minus 1 by 2. Therefore, Fourier cosine series equation will be f x, which is x sin x, is equal to a naught by 2 summation n is equal to 1 to infinity a n into cos n x. This is equal to f x or fx is equal to x sin x is equal to a naught has been found as 2. So 2 by 2 plus first term is, or it can be expanded as a naught by 2 or it can be expanded as a naught by 2 plus a1 cos 1x plus a2 cos 2x plus a3 cos 3x and so on. Therefore, fx will be equal to x sin x is equal to a naught is 2, so 2 by 2 plus a1 is minus 1 by 2 into cos x plus a2 means even, and for even we have minus 2 upon, so a2 is even, minus 2 cos 2x upon n square minus 1 means 2 square minus 1, then odd 2 cos 3x upon 3 square minus 1 minus 2 cos 4x upon 4 square minus 1 and so on. This will be the required Fourier series. Question 3. Now second part, putting x is equal to pi by 2 in equation 3, we get pi by 2 sin pi by 2 becomes 1 is equal to, this is 1, cos pi by 2 becomes 0 minus 2 cos 2 pi by 2 upon 2 square minus 1 means 3. Here 2 cos 3 pi by 2 becomes 0, odd pi by 2 0, minus 2 cos 4 pi by 2 upon 4 square means 16 minus 1 15, again 0, minus 2 cos 6 pi by 2 upon 36 minus 1 means 35 and so on. Thus pi by 2 is equal to 1 minus, this is cos pi is equal to minus 1, minus minus plus, so 1 plus 1 by 3, this is cos 2 pi plus 1 minus, here 2 by 3 minus 2 by 15, here cos 3 pi again minus 1 minus minus 1 plus 1 by 35, again minus 1 and so on, or 2 by this pi by 2 minus 1 will be equal to 2 taken common, 1 by 3 minus 1 upon 15 plus 1 upon 35 minus dot dot. Taking LCM, we get pi minus 2 upon 2 equal to 2. This can be written as 1 into 3 minus this can be written as 3 into 5. This can be written as 5 into 7 and so on. Or 1 upon 1 into 3 minus 1 upon 3 into 5 plus 1 upon 5 into 7 minus dot dot will be equal to, this 2 comes here, to pi minus 2 upon 4. This proves the second part, which is the summation of this series.